Can you go there and press on record?
Yeah. Sorry, guys, for being late. He just arrived, so he will introduce himself.
I don't know. Do I need this? Do I need this for the recording? Do I need a mic for the recording?
I think so, but why is not so? Hello. Yeah.
So do I need it for the recording? Because I think the room is not that big.
Yeah, try to use it. It's better than nothing.
Okay. Hello. Boom. Hello. Hi. Who? I think it's the handheld one. Handheld. Ding dong, ding dong. All right. I think it's this one. I think. Hold on. Bum 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 bum. This one. All right. Thank you guys for coming here. I don't know why I need a mic, but I'll use it. Appreciate your attendance. My name is Mircea Stancu. Some people in the industry know me as Miha, short and sweeter version. The reason why I'm here to talk to you guys is because I have some specialist knowledge in WASAD, Water Sensitive Urban Design. And, sorry. It's, you press this button here. Okay. And you put it.
You can directly
Put it on video.
Is it on now?
It's on now. All right. Sorry for that. So I understand that you guys are here to get some knowledge and insight on water sensitive urban design, which is another name for urban stormwater quality. I assume you guys are trying to learn a lot about engineering and become consultants or, I don't know, council officers or something like that. Or maybe learn and, I don't know, be part of the project management for a land development company. What I talk about is focusing a lot on land development. So the reason why stormwater quality modeling is implemented in Australia is mostly because of requirements related to land development. So if you think about it, when you build a new subdivision, and I assume some of you live in the suburbs, and even when you build a new high-rise building, like an apartment block, what happens is the guidelines require a lot of things, such as the roads have to be a certain width, the stormwater system for taking the water out has to be of a certain size. By taking water out, I mean just not letting it be in the subdivision, otherwise known as stormwater quantity. And part of the requirements for stormwater and for land development are stormwater quality requirements. In order to achieve these stormwater quality requirements, we need to do some modeling as per guidelines. These guidelines are what typically councils require, and there may or may not be state-enforced requirements. For example, in Victoria, there is something called the Victoria Planning Provision PP34, and there's a clause 56.07-4, and that clause says you have to treat the stormwater when it is discharged from a land development area because the government, in its infinite wisdom, has decided that not treating the stormwater will damage and pollute the environment. And the way you prove as a land developer consultant, or the way you approve something like that, is because you do some modeling. Another reason why this kind of modeling can be implemented is because you want to remove some of the water supply need. So you guys in Newcastle have Hunter water. Maybe Hunter water doesn't have enough water in their reservoirs. There's a bit of a drought, and they say, please conserve water. You may have experienced water restrictions. You can't wash your car, you can't water the lawn, and so on and so forth. This is because in a drought, obviously, we need to conserve the water. And in order to mitigate some of the water supply risk, you might want to put a big or small or medium-sized rainwater tank. Now you want to see how much demand you have from that rainwater tank, how much the rainwater tank can supply, and how big the rainwater tank should be to achieve a certain performance. Right? If you have a really, really, really big rainwater tank, it's going to cost you lots of money, and then maybe you're not going to get that much water from it. So there's a curve. There's a performance curve and a cost curve. The purpose of water sensitive urban design, as I discussed, I mean, I'm gonna freestyle a little bit, and the slides will support what I'm saying. Now, that's what can happen if stormwater quality is not addressed. Now, learning outcomes, understand what's the science and concepts, learn about the modeling inputs, gain knowledge on building and integrating a proper water treatment train, and learn how to calculate these things. All of this is required typically in your role as engineers for land development, or, as I said, if you want to build something that has to do with rainwater tank reuse. Cover topics, continuous modeling versus IFD data. Believe it or not, this is a fundamental aspect of stormwater quality and quantity, which is poorly understood to no understood by highly experienced civil engineers. Let me say that again. Many engineers working in this field do not understand the difference between intensity, duration, frequency data. It should be IFD, intensity, frequency, duration data, and continuous modeling data. I mean, any of you guys knows the difference or is familiar with IFDs at all? Yes? No? Hands up if you have heard of IFDs. Not at all. Intensity, frequency, duration data, 1 in 5 years, 1 in 1 year for UI. Haha, I caught you there. 1 in 5 years is not applied anymore. It has to be a 20% AEP, and that's not even 1 in 5 years, and 1 in 4 years and something. AEP versus ARI. Anybody knows the difference? That's okay. It's almost there, only to confuse you. ARI is average recurrence interval. So the expectation is that that rainfall will come every 5 years if it's 1 in 5 ARI. So he said, every 5 years, I must have one rainfall like this. Obviously, this is a bit of a misinterpretation, and again, the ARR in the infinite wisdom have decided to change it from ARI into AEP, and that is average exceedance probability. So instead of saying, it's been 5 years, there must have been one rainfall, that's 1 in 5, you say every year I have a 20% chance that this rainfall will happen. A rainfall of this magnitude will happen. You can learn about it and make your decisions if it makes a meaningful change in your civil engineering career in the future. Now, I must say, what I'm talking about here is extremely focused on, or I will try to be extremely focused on the things you need as engineers. The science behind it, I'm not really going to go too deep into it, because you guys, I presume, do not want to become academics. If you want to become academics, there's a lot of research that you could read, but the vast majority of people attending this course, I expect, will want to become engineers or some form of consultant or professional that works in government or councils or in consultancies or even in construction, building and implementing water-sensitive urban design devices, such as GPTs, bioretention, and so on. And I don't expect there will be a lot of academic interest, right? So maybe a little bit different than a typical lecture, because this is focused on engineering applied in the industry. And I highly encourage you guys to ask me questions. I'm very happy to answer questions. During this presentation, you can ask questions. I know it's maybe not super standard. Very happy. If I say something that doesn't really make sense or it confuses anybody, I love getting questions because I love sounding smart. And if I can answer your question, then I'll sound smart and I'll feel good about myself. And if I don't know how to answer the question, I love learning new things. So although I won't sound smart, I will find something to learn about for next time. So for me, it's a win-win. Please ask questions. And for you, hopefully, it's a win, because if you don't understand something and I can answer, you understand something. That's great. All right. So IFD data, that's an example. You have annual, as I said, annual exceedance probability, ARI. If you've heard ARI, don't worry too much. And we design an on-site detention system. So on-site detention systems, anybody familiar with them at all? Yes? No? Maybe? Yes? Okay. Hands up. Hands up. I need some visual confirmation. You guys are familiar? One familiar. Two. Okay. So on-site detention systems, obviously, you may have seen movies of old where you have a very rich person upstream and some the poor downstream, and then the rich person floods the poor, and then because they changed something in their environment, on their site, and nothing happens, right? In order to avoid this kind of social upheaval and problems, the rules and regulations state that if you do any work, typically increase the impervious area in a site, you will discharge more water, typically. It will be peakier. The discharge will be peakier. So if the discharge is peakier, then the downstream conveyance systems, by conveyance systems I mean swales, pipes, rivers, those conveyance systems will not be able to cope with a peakier flow, so they're going to flood potentially the people around those areas, right? So in order to avoid this kind of social disagreement and discontent, we will have, the standard is whatever change you do to your site, you can't discharge a higher peak. The peak can last longer, but it can't be higher. You guys familiar with that, mostly? All right. So this is, the IFD data is used for on-site detention system and also for the sizing of conveyance systems such as pipes, swales, channels, so on and so forth. When you have traveled, I assume some of you have traveled in places like Japan. Japan is a really good example. You walk through the city and often you see a very clear-cut concrete channel, pretty deep, and those concrete channels are designed to convey all the water from the built environment. Additionally, if you're fans of old sci-fi movies, you might be familiar with the very famous historically scene of the Terminator on the motorbike chasing John Connor on his little motorbike with a big truck. And what they do, they drive through the channels in LA, very, very big, or going even maybe older. You're the One That I Want movie, Olivia Newton-John. Greece, yes, in Greece. They do exactly the same thing. They drive through those. Thank you. Appreciate it. So what I like to do is connect the subjects of the lecture with hopefully some things that you know. So then you can get some understanding how it relates what we learn about with, or what we talk about with, how it relates to the environment. So going back to our IFD design rainfalls, these design rainfalls are just simply a value. You can see 14.6 millimeters in 5 minutes. That's unit is millimeters. You can see them in millimeters per hour. That is what's called the geogrid. All around Australia, Bureau of Meteorology has worked with CSIRO and others to come up with this data table for every roughly 2.5 by 2.5 kilometers square. Every 2.5 kilometers square, you have some other parameters and values. Are they correct? No, no. Do they even exist? Absolutely not. So these numbers do not exist in the real world. It's important for you guys to understand this. These numbers that you see here, provided by our sharp minds in the industry, do not actually exist. There are two methods of calculating things in stormwater. One method is based on this design storm. What does design storm mean? The design storm means that we expect that a storm about of this intensity will come every 5 years, yeah? But you can see for 10 minutes, you have a value, 22 millimeters. Do you think that the rainfall is going to go up, flat, and down? And that's going to be 22 divided by 10, whatever value per minute? Nah, that's not a real storm. Additionally, this kind of information does not care what happens before. Therefore, you have a rainfall, 22 millimeters, or let's go 20 minutes, 30 millimeters in 20 minutes. Again, it's not going to be flat. You have a 30 millimeters of rainfall falling on your site. Did it rain before? That's important. Has it been a 3 months drought? It's been a 3 months drought, especially if it's a pervious site like a pasture, right? So much you're going to get absorbed in the soil, of course. But wait, what if it rained yesterday? Well, the soil is already saturated. You're going to get discharged faster, right? So a different percentage of the water that falls on the ground will be discharged based on previous conditions. However, the methods for stormwater quantity do not look at previous conditions. Well. Typically, on-site calculation methods don't look, and you have a C, which is a coefficient of discharge that kind of says, okay, out of this, how much falling in, that much is going to be discharged. So what happens is this value is kind of statistical distillation of real data, right? Real data over 30 years has been like this. I expect this kind of intensity there, kind of in isolation. So that, statistically distilled, continuous data. This is continuous data. So if you look, there's a 5.5 millimeter rainfall in 6 minutes. This is at 6 minutes intervals, right, guys? So every 6 minutes, there's the way Bureau of Meteorology records this continuous data is every 6 minutes, water falls, and there's a little bucket, and the bucket tips. And it's like, okay, a little bit of rainfall. Great. We measure how much. That is the pluvio. It's a range gauge. The rain gauge does that, right? Technical range gauge little thing. As you can see, it randomly varies up, down, up, down. You don't really have any 30 minutes flat. 30 minutes will be 5 intervals completely flat. Doesn't happen. So that's continuous modeling. So there's a difference between IFD data, taking one storm in isolation that doesn't exist. The way IFD data is generated, you get all these rainfalls, and then you run some statistical analysis on it. And see, you could choose, that's a bigger rainfall interval. You could choose this part or this part or this part. You can move the values of the rainfall, right? It rained for half an hour. Maybe a part of that rainfall is 20% at 15 minutes. Get me? It did rain for half an hour, but I can take a subset of that. It's like, oh, this is a big rainfall for 15 minutes. And then the other 15 minutes is like 1 millimeter or something, or 0.5 millimeters. So I hope everybody is starting to get acquainted with this information. I can't stress this enough. Most people do not understand. Most civil engineers working in the field do not understand the difference. For real. I'm not joking. Water-sensitive urban design is based on continuous modeling because it relates to runoff over 10 years. Typically, it's done over 10 years. Can be over more. But how much volume of runoff do I have in 10 years? How much of that can I capture and treat? because all that volume is going to generate pollutants. I'm harping a lot about this because if you understand this fundamental aspect, everything else will be far easier. But if people struggle with this fundamental aspect, everything else can be really, really hard. Because people are starting to confuse in their professional approach quantity and quality. Very different approaches to quantity and quality. Both of them required by government, right? To give you an idea, there's almost no right answer in stormwater quality, almost no right answer typically from a scientific perspective. And why? You don't know what's going to happen. Can we predict the rain? Ah, man, I would be really rich if I could predict the rain. I'd buy or sell futures on wheat, right? I'll be fantastic. I don't have to come and do lectures. I'll just sit around and buy and sell futures on wheat, because obviously if it rains at a certain time, the wheat is going to grow. There's going to be a lot of crops, and if it doesn't, no crops. Yeah. So that's basically what's happening. The difference: continuous modeling for water-sensitive urban design, because you look at the entire amount of flow that comes over 10 years, and in transporting things, if you transport a 20% AEP storm, you can transport the 50% AEP, right? 20% means comes one in 5 years, roughly. 50% 1 in 2 years. Yeah. If you transport the 1 in 5, you can transport 1 in 2. Flat statement, and that's how typically pipes under the road are designed. In heavily built environments, you have the gutter, you have the it rains, collects the water from the road, goes into the gutter, and there's out of sight, out of mind. If civil engineers, especially water professionals, do their job right, the public will even forget we exist. It's kind of, the better you are at your job, the less respect you're going to get, because there's no problem. Oh, when there's flooding, then there's a problem, right? Let's call the water engineers to fix it. But if water engineers stormwater engineers do their job really well, there's never going to be any flood. It's just what's called transparent technology, right? When you write something on the paper, you don't think, oh my God, the technology in this pen, the big pen, right, invented in the 50s, unchanged for 75 years. You don't care about it. It's just your brain thoughts flow onto the paper without worrying about the paper and pen technology. It's transparent. Same when you walk on the street and there's a bus driving past you and you don't get drenched because there's a puddle. You don't even notice you don't get drenched. All right. So that's how continuous modeling, how continuous data is represented. You see that? On the left you have the rain gauge. In the next to it you have the year and month and day. And then you have 240 values representing every 6 minutes interval of that day. So it's 10 intervals per hour, 24 hours per day. And you can see here, for example, there's like 16, 14, 14, 12, all of that. So this is the table or math, well, it's not table, it's text file representation of that, of the blue line on the graph, blue lines on the graph. All right, so that's the difference in inputs for continuous events versus IFD data. Yeah, one is one value, which you can then back manipulate to make it to give it a temporal pattern. It's kind of funny when you think about, especially models like RORB, if you have used, or like big hydrological models. You get the IFD data and then you remanipulate it to make it look a little bit like continuous data. Honestly, to me, it's kind of hilarious. We get continuous, generate a number, and then deconstruct that number to make it something like continuous. Whereas continuous data is there. So rainfall runoff modeling. Any questions about continuous versus IFD, please? Or any other questions? Examples of different movies where you see a really big channel, concreted channel. All right. So no other, honestly, no questions? Great. Now, yep, yes, please.
Usually, how many stations for measure do you need, like per 100 kilometers, to know the continuous?
Ah, that is a very good question. I have, with my colleagues, have created an algorithm to do that. Maybe I can, let's hold on to that. So it's not what you need, it's what you have. So Bureau of Meteorology has come and put a lot of rainfall stations all around Australia. It's about 10,000. Back in 2021, I bought the data for all of them. So on one of our tools, Bomb the Builder. Bomb, Bureau of Meteorology, not Bob, please. So on one of our tools, you can see there's a map, and then there's like all the rainfall stations. And Bureau of Meteorology, again, in their infinite wisdom, decides where to put them. It's important to kind of look at what climates there are and also how many people will live in that area, right? So if it's out in Whoop Whoop, I mean, who cares? You know, it's like, oh, it didn't rain for the kangaroos. Big whoop, you know. But if it's, you know, in Newcastle or in Melbourne or in Sydney or in Brisbane, I mean, if it rains, or Cairns, I mean, not Cairns, but the rest. If it rains a lot, and you need to understand kind of what happens there so you can protect the assets and people's lives from, like financial assets and people's lives from flooding. I hope I have time to circle back to that, and I'll show you. Now, rainfall runoff modeling. Are you guys familiar with rainfall runoff modeling? Okay. Are you familiar with the rational method? All right. Who can tell me the formula for the rational method and these? It's four parameters in that formula, or 4 variables in that formula. It's kind of like E equals mc squared, but with like an extra value. Q, the flow, Q equals? Yay! Who said that? Did you say that? Oh, you said that. Oh, sorry, I thought Tsanging cheated. Thank you very much. Q equals CIA. That's literally a rainfall runoff model, right? I mean, it's a basic one, but runoff. Flow equals C, coefficient of discharge, I, intensity of rainfall, and A, area. Rainfall, I, over the area, runoff Q, as a model. Q equals CIA is a very simple rainfall runoff model. In WASAD, I mean, in RORB or others, you have other CL, IL, and all that. Again, because CL, I think, is well, initial loss and continuous loss, right? Again, because they're more simple, you have to have one parameter for that rainfall that you have, and you don't go continuous. In continuous modeling, the rainfall runoff modeling, Cho McMahon 1996, is a little bit more complicated. So what's happening, you have rainfall falling on the surface. That rainfall, every 6 minutes, we have a bit of rainfall. I mean, you can look at it at continuous data at 6, 12, 30 minutes, 1 hour, so on and so forth. But we typically go to the lowest time step we can because it's better granularity, yeah? 6 minutes of rainfall falls on your surface. Then there's a model of leaky buckets. Some water goes in, gets stuck in the root zone. Further, more water goes in, gets stuck in the zone under the root zone, and then those things some water that gets stuck in the root zone that never leaves because the plants take it and it's just like a sponge, right? It never leaks. But then some of the water generates base flows, which are subsurface flows, and then they come up somewhere. You typically have, if the groundwater level is low, you have that kind of flow. You find it in the stormwater pipes. You look at the stormwater pipe, it rained like 5 days, not 5 days, like yesterday, and then you look and there's still some base flows through there. Like, well, why is this not dry? Because it hasn't stopped raining for 15 hours. Those are the base flows. So the soil acts like a sponge and discharges slow. And some other water is lost through groundwater, right? So that's the rainfall runoff model for pervious areas. As you can see, a little bit more complex. For impervious areas, the rainfall runoff model in the John Connor Online and Music Engine. So John Connor Online is our software. Music is Iwata software. I used to work at Iwata for a while. This kind of, but all the data for the engine is public science, right? So if you, those of you who go into academia and really want to know, you can go on the Iwata help webpage and then help site and just keep reading until you really fall asleep about 20 times. But that's for academic purposes, right? To understand the underpinnings of the model, you typically wouldn't care about that as a civil engineer. I've never met a civil engineer who was really concerned about the scientific underpinnings of the model. I'm just conceptually sharing with you guys kind of what happens. So if you have a pervious area, a lot of water gets lost and the flow generated is not that much. Some of it is overland flow. It's called storm flow. Some of it is base flow. And that's how the water goes. In the impervious area is very simple. 1 millimeter is lost in the interstitial spaces, like on the road or on the roof. For example, you go outside, you buy a bottle of water, and you put it on the, you dump it on the road. That water is not going to go into the drain, right? It's going to make a little bit of a wet patch, and that's it, because some water is lost in the interstitial spaces. So if there's 1 millimeter of rainfall a day, it's going to generate no runoff, because it's lost, right? It just gets stuck there and then evaporates. Oh, cool. And then the rest, all of it is discharged. And that water that is discharged is going to have some pollutant. From the pervious area and from the impervious area, all of it will have some pollutant. Clearly, not so much from the pervious area, unless it's agricultural land, which you guys are familiar with. You know, they dump a lot of fertilizer and stuff. But assuming just a lawn, some water is discharged, not so polluted. The roof, also not so polluted, but somewhat. Sorry, and the road obviously will be far more polluted. As you can see, a little bit of total suspended solids in there, if I'm not mistaken. Huh? Maybe. Any questions about rainfall runoff and all that? You guys are familiar? Yes, no, maybe a little bit, yeah. Obviously, in a continuous model, the landscape gets increasingly wet the more it rains, and increasingly dry the less it rains, right? So there's that time component of the soil absorbing or not the water. Tell me if it's too simple. I can make it more complex. Now let's look at pollution generation. Pollution generation in your modeling, right, is all about what? Believe it or not, guidelines. And this is probably when I should talk about engineering approaches to doing your job and the rules. Engineers have to follow some rules. And the rules are like that. The rules of man, humans. Man as a general, right? The rules of man say you have to follow the law. The law says this, the law said that. Sometimes the laws are very, very wrong, right? Very wrong. But you have to follow them, otherwise your peers will punish you. Many, many, many examples of historical situations where the rules of man were wrong. Slavery is one, but I'm sure there's many, many others, right? If you free somebody from bondage, you will be punished, right? Because you shouldn't do that. Why? Because the rules of man say that. In engineering, the rules of man are the rules, guidelines, and regulations that allow you to keep practicing and not to go to potentially go to prison for gross negligence, right? That's in engineering. You can't, like, if you do something that's not in accordance with the rules of man, you might get anywhere between a slap on the wrist and a slap on the slammer. So that's important. As you can see here, we can see the pollution generated. You can see it there. The real pollution is generated by the rules of a denominational God, non-denominational God, Spinoza. God of Spinoza, which represents the natural world, the universe, the rules of the universe. So if you build some water devices, water quantity, for example, you can size the pipe in accordance with what? You can size it in accordance with the rules of God. But if that does not comply with the rules of man, you're going to get in trouble because people are going to get flooded, people are going to get hurt, potentially drowned, and guess what? Somebody's going to cop it. So because of that, in civil engineering, especially stormwater, any stormwater rules, or any stormwater engineering, unfortunately, the rules of man take precedence to the rules of God. If you want to build a rocket, like our friend Elon said, you can't sue your way to the moon. The rules of man are kind of irrelevant because the rocket blows up, or it doesn't, and goes up, or it doesn't. The rules of God are far more prevalent in there, right? But in stormwater engineering, the stormwater is way too variable, and the things that we do are all to protect our fellow man and their property, which means that you must apply the rules of man. I share this with you because when you go into your workforce, this is probably one of the biggest lessons you really need to learn very quickly. We do things in accordance with the guidelines. My approach to whenever I do engineering is whenever I do a report or a design, if I go to court, can I defend this? Will some of my peers at least agree with me? Cool. Will my peers disagree with me? Problem. That's my highly risk-averse approach. You guys choose how you do your approaches, right? And sometimes the company chooses for you, but or the superiors. So going back to pollution generation, every single authority either has or should have pollution generation value. So when it rains on a roof in Blacktown City Council in Sydney, it generates a different amount of pollutants than when it rains in Liverpool, although they, I don't know, or whatever, Parramatta, whatever neighboring councils there are, believe it or not. Council in Blacktown has a certain pollution generation value for their roof and certain types of surface areas that generate pollutant. Other locations different. It varies. Again, I was surprised in the past to know that students did not or were not aware with the fact that guidelines exist. I did have an intern and I asked, do you know how to build a music model? Sure, it's super easy. Great, show me. He could build a music model, but it was absolute garbage. Wrong continuous data, wrong source nodes for pollution generation, completely absurd treatment train. Oh yeah, you can build something there. Sure. It's going to be completely useless. Very, 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 very not useless. And if the answer is, well, at least I built something, it's similar to me saying, design me a rocket that can take me to Mars, and you design a rocket that's the size of Earth. I mean, I can't. What am I going to do with that design? Nothing. It's completely useless. So it's important to think about that, the quality of the work that we do. So we talked a lot about pollution generation, and then I'm going to tie it back in and say the continuous rainfall data is something in music you have to put in accordance with guidelines. In John Conroe line, it's already loaded up. Pollution generation and type of source nodes is something that in music you have to put in by hand. In John Conroe is already loaded up. And the pollutants that we typically, that are calculated in these models are gross pollutants, total suspended solids, total nitrogen, total phosphorus. Total suspended solids is that in the middle, which you can see, or that to the right, turbidity, right? Turbidity tells you how much total suspended solids there are. And then nitrogen and phosphorus are nutrient compounds. It's total because some of them are stuck to the total suspended solids, some of them are in free forms, dissolved, and they're harder to take out. Dissolved nutrients, total phosphorus, and nitrogen. Various speciations, right? Various compounds. Total suspended solids and gross pollutants. Anything that's less than 5 millimeter is a total suspended solid. Above 5 millimeter is a gross pollutant. Any questions? Yes, no, maybe. I'm happy to take questions. I don't want you guys to get bored. Ask me anything. Okay. Reddit AMA, right? All right. If you are wondering if the gross pollutants sit into the gross pollutant trap too long, you're gonna end up with this, which is very, 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 very bad, totally not good day. The gross pollutant traps, especially the wet ones, which is most of them, if not all, regardless of what some manufacturers say. There may be one or two that are not super wet, but the leaf matter, sticks, and other leaves and other things just sit there and decompose. So instead of having a leaf that you can pick up and throw away, you're going to have a lot of dissolved material that's literally just turns the water green or a variety of colors. None of them good. So now we learned a little bit about the base data that you put into the model, which is the continuous rainfall, typically for 10 years. Some councils say 20. Most of the councils tell you which data you should use. After which, you model your site. I have this much roof, this much road, this much landscape. And that's going to allow the model to mathematically calculate rainfall runoff. Now, after the runoff, you might want to treat it. And you have different treatment strategies. If you have a particle size of 5,000 micrometers, like 5 millimeters. 5 millimeters and above, that, as I said, gross pollutants. Now, the modeling engines that we have, John or Music, because John and Music basically do the same, not basically, they, from a results perspective do the same thing, but from an engineering perspective, I believe John is far, far easier to use as an engineer and get you there faster and much better, in my opinion. So everything that's liter above 5 millimeters, we don't have any way to calculate the reduction. So what you do is just put a gross pollutant trap there, and then the manufacturer comes and says, this gross pollutant trap is going to remove this much. So you have this gross pollutant trap. I believe this might be a CDS unit. The CDS unit, they have done some analysis, and they say, okay, out of the gross pollutants, it's going to reduce this much, TSS this much, TPTN this much. Other devices have other reductions, so you just put them in there by hand. If you have Music, if you are John Caroline, you just choose it from a table of accepted by council devices, because the council has to accept them. And believe it or not, you will find this to be very entertaining. Some councils have their own specific reductions for the device. For example, Blacktown Council says that GPT is going to reduce, I don't remember, but let's say about 23% of nitrogen, and the council next to it accepts the manufacturer's claim of 45. It is what it is. That's what we're going to do. As a civil engineer, your role is not to question the council too much. You can question the council if you've done everything in accordance with council's guidelines. And then, if the council officer does not really know exactly what they're doing, you say, I've been to that guy's lecture, and this is what happens. You have to do it this way, because this is not your personal company. You are an enforcer of rules, regulations, and guidelines. Similar with the police. Police can't beat you up, right? As much as they would like to, because they're supposed to enforce the law, not do whatever they want. Kind of similar. But if you do not comply with the council's guidelines, you're going to get a request for information, and you're going to waste a lot of time, and then put the time against your timesheet, against the project, and your boss may or may not be very impressed. Probably not. So think about it all the time. What we do in WASAD typically is a commercial endeavor. You can't spend too much time on it just because you're on a fiddle, and you can't really do a lot of testing, blah, 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 because that costs money. Now, if the land developer wants you to do it this way and says, if you say, hey, it's going to come up back as an RFI, they'll be like, okay, if it does, it does. I'm like, okay, cool. Whatever you want, dude. You're the client. Right? Obviously, you can't do things that are against your ethical requirements, so it gets a bit more complicated. So, particle size, gross pollutants, treatment process. Screening is very, very high hydraulic loading, which simply is a fancy, very fancy way of saying small device, big flow. Doesn't take a lot of space, relatively cheap to treat a lot of flow. Coarse to medium, so 125 micrometers to 5,000 micrometers basically is like sediment, very high size of sediment. Sedimentation pond, enhanced sedimentation, adhesion filtration, biological uptake. As you can understand, the smaller the smaller the particle gets, the harder it is to take out. Therefore, what you need to do is a treatment train. Choo-choo. You guys familiar with treatment trains at all? Yes. 1, 2, 2, 3, 4, 5. Okay, cool. Oh, awesome. Thank you. So when you have a treatment choo-choo, what you do, you first put in primary, secondary to remove the left side, the top side, and then secondary, tertiary, and then tertiary if you want to polish it off. Example of primary, secondary would be a gross pollutant trap or a sedimentation pond. Although sedimentation pond, in my opinion, shouldn't be used as primary because you get a lot of rubbish in there, right? Secondary, tertiary would be a bioretention. Sometimes bioretentions are used for primary as well. Go to our, if you would like to, go to our website, cleanstormwater.com.au or stormupdated.com.au, and if you go to help, you're going to see all of these, the things that I'm telling you guys, you're going to see those. Treatment train, catchment, primary, secondary, tertiary, and a list of and data table of what does what. Very focused on engineering, right? So primary, secondary, tertiary. You can have all three, and obviously rainwater tanks are a little bit separate, and we might talk about them later. But this is the order in which you should treat them. If you have a GPT and then another GPT, big no-no. Some people do it. Some councils don't call them out on it. Some councils never even check your music model. They know who they are. Some councils will have ridiculous requirements. You may choose to fight them or not. Typically, as young engineers, you will respond to your bosses. So it is what it is. You may want to do the right thing, but sometimes the right thing might be advised to you that is the wrong thing. I cannot advise you in any way, shape, or form, because you might want to keep your jobs and not tell me that you've listened to my advice. So a little bit cynical there, but that's how life is. Any questions about the treatment train, devices, how they should be employed, all of that? Why not a GPT after another GPT? Oh, please. That. Very simple. When the water comes from the catchment into the GPT, the testing of the GPT was done with a certain quality water, which is right after the catchment, right? And then the values of the reductions that you put them in manually. The model doesn't do anything with it. It just says, okay, 1 megaliter of water comes in, it's got 1,000 kilograms of TSS, your reduction is 70%, boom, 300 come out. Done. It doesn't do any analysis on it at all. That's specific to GPTs. If you put another GPT in, you're double dipping. Because the water that comes out of the GPT is far cleaner than the water for which the GPT was tested. So that reduction is not going to be the same, is it? Because all the particle size distribution on the, obviously bigger particles get cleaned up faster, smaller particles not as fast, right? So out of those 300, maybe 250 will be very small size, right? You see what I mean? So then this reduces 73% of the full distribution, not only the small size. The small size may reduce very little. So if the water that comes in is at this level, mostly, instead of a good distribution around, then your reduction will be different, right? Typically, surface area versus volume, right? And versus mass. Volume as a proxy for mass. If you have 5 millimeter rocks and 1,125 micrometer rocks, which one's going to weigh more? Probably the 5 ones, right? Because if you can break the 5 ones into, each one of them into 1,125 micrometers, right? So because of that, all the mass that comes out is typically very, very small size. The second GPT is not going to be able to remove that. So that's why. You completely change the conditions in which the GPT was tested. Was that it or another one? Okay, cool. Any other questions? No? Yes? Maybe? All right. So how are pollutants generated in, and I encourage you, instead of saying WSUD, I encourage you to say WSUD. Please try it yourself. WSUD. You can try it, and I'll tell you why. If you go and talk to anybody who has knowledge in the industry, they will be very snobbish if you say WSUD. So, oh, you don't know anything. But when you say WSUD, it's like, yeah, mate, WSUD. No, it's going to be a different approach. So that's what I encourage you guys to do. You can test it if you want. Pay attention and test it if you want. So every time of catchment runoff, stormwater pollutants are generated for that runoff stochastically. Oh, man, I don't know if I have time to tell you about stochastically. Stochastically means it doesn't matter. Okay. With a notable exception of rainwater tanks, please, 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 if anybody tells you about first flush in music/JCO modeling, don't believe them. They have no idea what they're talking about. Key for you guys to know they don't have any idea what they're talking about is stochastically. Anybody knows what stochastical means? Haha, you're a researcher. Can you help me? Stochastical. Stochastic. It's random. There you go. Pollution is generated randomly for every rainfall event, for every time step. And I'll tell you why. Let me go back and I'll share with you the reason why. The reason why is this. As you may notice in this particular location here, there's been a little bit of a drought. And then you have really big rainfall, right? Based on this, I don't know. Maybe that drought was like 2 weeks. In 2 weeks in Newcastle, if it doesn't rain at all, do you guys experience a little bit of dust? Yes, no, maybe? A little bit? Okay, a month it doesn't rain for a month. It's pretty dusty, right? It's not that nice. In my background is Romanian. In Romania, sometimes they have like, I don't know, 28 days of 35 degrees or 33 degrees plus. Gets dusty. When that water drops, a lot of pollutant, right? It's going to carry everything. So what's the concentration of rainfall in this high intensity rainfall is going to be? Pretty high, huh? I reckon. Now, or let's look at this one. Pretty high here. And then there's a little bit of drizzle right at the end. How high is the pollutant concentration going to be in that drizzle right at the end? Basically nothing, right? It's going to be pretty clean. All right. So what that means is that there's no such thing as first flush because we don't have a specific rainfall event like a 1 in 5. I'm circling back to the 1 in 5. The model in some people's head is, oh, it's a 1 in 5 year rainfall. Therefore, the first 2 minutes of the 1 in 5 year rainfall are going to have a lot of pollutant, and then after that, no pollutant. Because they don't think operationally or time. Another thing that I highly suggest to you guys to try and do is very hard, very hard. It took me 35 years and I'm still trying. I started at 10. Think of things operationally. Step 1, step 2, step 3, step 4, step 5. It's very hard. And then if you change step 2, what's going to happen? Change step 2 and step 3, what's going to happen? It's very hard because you get exponentially more options. Right? But if you think about things exponentially, and the model of the world that you have is exponential is operational with all these exponential options, then you kind of start to understand step 1, step 2, step 3, step 4, and then hopefully it's going to be easier to say, no, there's no such thing as a first flush because you don't even know when the rainfall is going to come. It's all continuous. And I'm not saying that. The research that our engines are based on says that. Duncan et al. 1999. Tell me and I'll send you the paper. I mean, for those of you who have insomnia, it's a very good cure. That's in the help file. And I still have to argue with people with 25 years experience who keep on talking about first flush. It doesn't exist. There's no such thing in the context of stormwater modeling. And another important part is that, should I talk about that? Stochastically goes around the mean. But the stochastic value is not the actual concentration of pollutant, is the power of the formula. So the concentration of pollutant is logarithmically going higher there than there. So one standard deviation to the higher pollutant is like 1,000. So if your middle is 100, one standard deviation to the higher pollutant is 1,000. One standard deviation to the lower pollutant is 10. So on absolute values, if you replace stochastic generation with mean generation, you're going to generate far less pollutant. Get me? Because if you vary it on a curve that's like really steep, really flat on that side and really steep on this side. You choose randomly on those two values. It was a very hard lesson to learn. Here you got very fast, something that it took me about 5 months to get. All right, so we were talking about stochastic generation. There's no such thing as a first flush, with the notable exception of rainwater tanks. And I'll tell you about rainwater tanks. When you put a rainwater tank, water comes in from your roof. You don't do the first flush in the modeling, but you do install a first flush device. How does a first flush device? It's a big tube with a ball and a little drip at the bottom. Water falls in, fills up the tube, lifts the ball reaches the top and isolates it, and the water goes into the tank. Why does it work like that? It's because if it didn't rain for a while and then you have a sudden rain, you want to capture as much of the sediment as you can. You're familiar? You have a rainwater tank at home, or okay? Maybe some of you guys have rainwater tanks at home and they have first flush devices. Look kind of funny, like a cylinder with a little pipe at the end. And that empties over like a couple of days, slowly, or one day. Typically they're like 50 liters, 100 liters. I think typically they're like 50 liters per 100 square meters of roof or something like that. That's for your detailed design, right? You should know that there should be a first flush device. And also typically the rainwater tanks, you don't put in the modeling, but they do have a net to catch gross pollutants. All right, there you go. Get the PowerPoint and you'll see. See, that's exactly what I meant with goes too far, and stochastic, blah, blah, blah. Actual concentration and actual mean. All right. All right. Any questions about the pollution generation that's stochastic, random, around the mean? Yes, sir. Yes, sir. Man, that's why I didn't want to talk about it. All right. So when you say there's a stochastic generation of pollutant concentration, when we talk about pollutant, it's pollutant concentration in the water. So if you have 500 ml of water, and this one has 5 pieces of sand in it, it's going to have, 5 milligrams of sand per liter, right? If it has 10 milligrams of sand. You get me. So it's concentration per volume. And the computer says, okay, the mean, the average of the pollution concentration formula is not the average of the actual absolute 5 or 10. But when you generate it, you use like a little bit of a formula, right? So the average of the formula is 10. But on the formula, draw parameters apart from the variable, which is the log. So you vary the variable. You don't vary the things at the bottom, right? So when you vary it, and you have a standard deviation of 1 from 10, like this is 10, right? The mean is 10. So the mean of the log is 1, which means the mean is 1, so it's 10 of the absolute value. And then if you make one standard variation 10 to that side, is 100. You turn it to 0, is 1. See? So that's a log distribution. So the mean is not the mean of the concentration, it's the mean of the one parameter in the formula that determines the concentration. Does that make sense? It's not the mean of the absolute value. Don't at me. This is what these guys came up with. I'm just sharing with you the science that they came up with, right? I didn't come up with it, but I know about it, right? Yes.
The actual value does not follow normal distribution. And if you log transform the actual value, it will become a normal distribution. And that can help us to do the model. So when you see that graph in the top right corner, it's a normal distribution. And they calculate the log mean is you log transform all of the actual values, and you get a new set of values, and then you take the mean of the new set of the values. That's the log mean.
Anyhow, this is not going to be that important in your life. You're not going to care about it. So that's why I kind of didn't want to go too deep into it, because for you guys as civil engineers, oh, it's cool to say about, like, for a coffee, it's like, you sound smart, right? But it's really, and you will be, but informed. But for your design, it's got near no. What is important for your design is to know that you don't size the intake for your device based on IFD data, because IFD data is irrelevant for the purpose of continuous modeling. So people say, I'll do the music model, and then after that, I'm going to size up my intake to my GPT based on 1 in 3 months. No. Because then, if you change the high flow bypass, that's a characteristic of the music model or JCO model, so you have to run the model again, because that high flow bypass tells you how much volume you're going to get into your GPT. And I had a very interesting chat with your lecturer, a standard lecturer. And Tsang-Ying said, but if it's bigger, then it's better, because I'm going to treat more. And I said, not really, because I'm going to pay more. I don't want to pay. I want to achieve the targets. You're the consultant. You should achieve the targets. So if you do the music model, and then you put the high flow bypass 1 in 3 months, also known as 4EY, if your high flow bypass is decided based on 1 in 3 months, but your model is done with no high flow bypass, wrong. No. Why would you do that? You have to rerun the model. And look, if you run the model and you have it, if you have a flow lower than the high flow bypass, lower than the 4EY, a high flow bypass, how much water goes in, how much water goes around, then your GPT will be smaller, so you save your consultant money. But then, if you need a bigger one, right, a bigger high flow bypass than the 4EY, then you have to do that, otherwise you'll shaft the environment. No? It's kind of easy. Well, theoretically. I mean, people don't understand that. Many people don't understand that. Why? Because they don't understand the difference between IFD and continuous modeling. That's why I kept on harping about it for half an hour. And if you look on our help page, there's actually a paper that I wrote specifically so people understand the difference between IFD and continuous modeling. So, this is a typical, well, it's not really a train, it's like a locomotive. That's a GPT, an ecoceptor, catchments, flow generated from continuous. This is the John Conroe line interface. As you can see that that car park is car park, there's road, that is a roof, obviously because the roof is colored. And if you are kind enough to zoom in, it's a little dog here, just to help everybody feel happy. And that's a landscape, beautiful landscape, some flowers. And they all go into an ecoceptor. The ecoceptor is a native node. You don't have to build it or ask for the manufacturer to give it. And if the council accepts it in that location, it will be available. If the council doesn't, it's not available. So there's some significant changes from the John Conroe line interface with the music interface, because John Conroe line interface only lets you build things that council accepts, and the parameters that council wants are already integrated. Right? So in music, you have roof, road, and what are other type of nodes. Don't use them, they're wrong. Please. You know how I know? I put them in. For real. In the software back in 2016, I put them in. I went to the developer and said, these are the values here, 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 here. And why are they wrong? Because the roof pollution generation varies per council. The road pollution generation varies per council. There's some rules. For example, this is in Victoria. The car park road has to be 100% impervious. Victoria doesn't give you pollution generation for base flows, which is the part of the permeable area. So roof and road 100% impervious. Must be. You can't build anything. Like if it's a balcony and people walk on it, it's a road. According to music modeling water guidelines. Melbourne Water Music Modeling Guidelines, originally 2018, now 2024. You guys as civil engineers won't have time to read all the guidelines. Highly recommend you use a tool like John Online or others. Because otherwise you're going to have to put everything, every value in music by hand. You're going to make mistakes, for sure. Ask me how I know, because I used to do that a lot. I used to make a lot of mistakes. So catchments, flow generated, pollution concentration, pollution inflows device, flow treated by device, residual pollutants from device. Huh? Okay, kilograms per megaliters per year. So pollution inflows 120, that removes that much. In outflow from device, pollution reduction. Okay? Does it make sense? This treats 0.48 at a certain reduction, blah, blah. It's literally water comes into the device, high flow bypass decides this amount of water goes into the device, the rest goes around. So you have 100 liters a second going into the device, and that's a 30 liters a second device. 30 liters a second go in, and 70 go around. It's called a high flow bypass. All right, so this is the end of this presentation. I have more information. But ask me things, please. Yes?
Why there is no general rule follow? Like for it's very.
What do you mean?
Like you were talking about each council they have their own rule for pollution.
Oh, and devices that they accept. Some councils accept this. Why is there no? Oh, beautiful. Can I tell you a story? I will tell you a story even if you don't want me to. And you like it. Internet doesn't work here. Internet. I will tell you this story, and please connect to the internet and I'll show the guys. So I'll tell you this story, and you guys, I hope, will appreciate the irony, because I did. It was hilarious, but also a little bit like, come on, guys. I have also in our software, in our website, there is there's on-site detention calculators. You can calculate the on-site detention via a simple method, like the rational, modified rational, Swinburne, Boyd's, or you can calculate on-site detention with more complex models like RORB or WBNM, or occasionally drains or others. And each council has a preferred on-site detention calculation method. In Queensland, it's typically rational or modified rational. In Victoria, it's typical Swinburne. And when I created the tool, I just wanted to, you guys can see my view. You have to build all the guidelines into the software so the civil engineer doesn't need to read guidelines. I have a significant disdain for reading guidelines, and many of my colleagues disagree. But my view is this. In the guidelines for music modeling, a bioretention, orthophosphate content, and total nitrogen content for the filter media in Queensland can be 400 and, no, well, orthophosphate, 30 and 400 respectively. The defaults are 55 and 800 respectively. And in Melbourne, it used to be 50 and 800, but the 2024 guidelines changed them to 30 and 800. I don't care. You shouldn't either. It's a small parameter in some rubbish software. Like, who cares? Honestly, why do we need to read 100 pages of guidelines to figure out, oh, this parameter is this, I'm going to go and put it by hand? It makes me mad. I don't hope it should make you guys too. Back when I was in uni in 2000. I like computers, right? So I did my civil engineering degree before I did my artificial intelligence degrees, but I still like computers. So when I was in my civil engineering degree, I was building computers and having LAN parties and all that. It was all the rage, right? And I remember I was getting my friends to come, and it would take us 3 hours to set up the network. Like, let's have a game, you know? It's like, okay, they come at 8, by 11, we're like, okay, we have a LAN working. You might, right? I know, those of you who maybe work on Linux might know that. Now, what do you do now? Click, done. No DCP connection setup, no IP setup. You don't need a router. You don't need to figure out that you need a cross LAN Ethernet cable. We used to build our own cables, and if you go computer to router is straight. Otherwise, you have to cross a couple. It's so complicated. Now, Wi-Fi, click, done. That's what I'm talking about. It's like people in the DOS time saying, oh, if you make it Windows, people who don't know anything about computers are going to use computers. Yes, because what you need to understand is engineering, not how to use the software. What you need to understand is concepts. What I've been talking about with you guys here, I was trying to mostly give you like the understanding, not the underpinnings that this value is X and that value is Y. Who cares? I am significantly against the idea of having to read guidelines in detail for specific information like that. And some other engineers, no, but you have to read the guidelines because that's our value as engineers. No, you have to understand what's going on. You can skim the guidelines, which you would do anyways. I had a colleague in uni who was like, I read the standard every day. I'm like, bro, no. Anyway, so to go back to my story, to answer your question, I was talking to people in Tasmania, and I called the council and I said, what on-site detention method you guys want to prefer so I can make it the default in the software. You go to that latitude and longitude, and it knows what method you want. No, hold on. No, my first question was about stormwater quality. There's no standard guidelines. Each council has the same guidelines. And he said, yes, this is bad. There should be a statewide guideline that is like exactly what you said. Everybody should have the same rule, blah, 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 blah. We had a like 5-minute discussion about why there should be a statewide guideline. And then I said, okay, but what I'm calling you is like on-site detention. What method do you want? Because your colleagues at upstream want the rational method. And I swear to you, 30 seconds after that big discussion, he says, yeah, but we prefer things our way. Cool. All right. Do you have your answer? I don't like it. So this is our software. So if you go, guys, if you go to here, you can see here, big there, right there, distinction between continuous IFD, pollution generation modeling, first flash relevant, exactly what I... So I've written this because these highly experienced people kept on talking about this nonsense. Key features, all that. We have some tutorials, you can watch these, and this is a list that I've done a long time ago, like a playlist that I think will explain a bit even more about how to use things. But I will share with you. Hopefully this works. All right. So I will share with you one of the methods. Oh, where are we going? Okay, let's go here. Doesn't matter. So you asked me about how many rainfalls, yeah? That's Bomb the Builder. So this is Bomb the Builder, which has a data set of all the rainfall stations. Now, you go here. That's how Bomb put them in. It's like, again, They had it, we bought it. That's the 6 minute. They have other gauges, but these are the 6 minute ones. And another interesting aspect of BOM, you can see the meteorological templates. A meteorological template is that continuous rainfall data that I told you about, right? So that continuous rainfall data, being the meteorological template, it is the first step to your modeling. You can't do model without the meteorological template. It's just not possible, because you don't have the base data to run the mathematics on. And the meteorological template gives you rainfall at 6 minutes and potential evapotranspiration. Why is potential evapotranspiration relevant? It's not super, doesn't have a super high impact, but so it's relevant for the following reason. You have an amount of water, a sediment basin or a wetland, has a certain surface of water. And it doesn't rain, but it's hot. Some of that water evaporates. You have something called NOL, normal operating level. Normal operating level is the level of water, right? Nothing happens to it. If you don't evaporate, it just sits there forever. Then you have the extended detention depth. What does the extended detention depth mean? A wetland has a small orifice that allows the water to drain slowly. A sediment basin has also a small discharge orifice that allows the water to discharge slowly. When water comes in, extended detention depth is the space from null to the weir overflow. That allows a volume of water to be stored and treated by the device. Does that make sense? All right. So you have normal operating level, but now if there is drought, it drops. Right? So if you have a little bit of water coming in, it can raise, but it doesn't even start discharging because the evaporation made it drop. And that allows you to have a better performance, because all that pollutant that came with the water, gone. What the model expects, and don't ask me, I don't necessarily agree with the model. What I'm sharing and teaching you guys here is what? The rules of math, okay? So I'm showing you what the model does, how it represents reality, where it may or may not agree with reality, and what the model assumes. I'm not saying the model is right, I'm not saying the model is wrong. But the model is required by the laws of man. So if you guys want to work as civil engineers, you have to follow that. If you want to be inventors, that's a different story, absolutely. I'm fully supportive of that. The AI is going to come in 5-10 years, and then we can all invent whatever we want just for the fun of it, for the giggles, right? Every single drop of water that's taken out of the system takes its corresponding pollutant concentration with it, right? So yes, that's the webinar. Okay, so yeah, I wanted to show you something else, which is these are the meteorological templates all over Australia. And now we have, I can show you the evapotranspiration annually. That's remember I told you guys about the geogrid? This is a geogrid, every 5 meters, 5 kilometers, 2.5 kilometers, sorry, see? That's a drop, 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 drop. There's boxes. That's what the geogrid is. And that's the evapotranspiration, and when we create a meteor template, we pick the evapotranspiration per month. Now you might find this amusing. The software developer who coded this made the colder evapotranspiration red and the hotter green. It is what it is. I haven't changed it, it's fine. Then you can see here rainfall, annual rainfall. That's typical annual rainfall all around Australia, or you can have it per month. And actually you can edit your scale if you want. So that is BOM the Builder, and with BOM the Builder, with BOM, we build. Worker clouds in service of the motherland. Why not? What we typically do in stormwater quality is boring. You may have noticed. So I am trying to have a little bit of fun, so you guys don't fall asleep. So you can create a methodological template here. Hold on. What's happening? I'm going to restart. You can click anywhere, and you should be able to create a method template. And I'm going to create one at, let's say, 5 years. And I'm going to overlap on it the IFD data. And I'm kind of showing to you guys how the rainfall, like this is generated in accordance with an algorithm that I invented. I asked people to tell me if it's, I've had questions about the algorithm. I said, well, this is kind of what I came up with. Why, do you have a better idea? I'll change it. And none of them said anything, so. So this will generate that data set that I'm talking about, and you can apply climate change to the data set. And if you want to, I highly recommend, this is free. I highly recommend, I think it's free, going and reading the climate change algorithm and the webinar. I think you will like, well, if you have interest. Again, nobody else came up with this. I don't know why, they should have. For 5 years, this is a cumulative graph. All the rainfalls that are under 68 millimeters an hour, 6.8 millimeters a second, if you add them all up, they are 98% of the entire rainfall. So remember when I said the high flow bypass, if you set it at high, you set the high flow bypass, where do you set it here, right? Wherever you set it, you have to capture enough of the volume to make sure that the pollutant targets are achieved. The green lines are on top of it, right? You see that? I just created this graph. I never created it here before. It was just random. So all the rainfalls under this value are under 1 in 3 months. Consider. I think it's pretty cool. I'm pretty proud of it. And if you want to, you can actually adjust it based on climate change. Again, based on a certain algorithm. It's pretty cool stuff, if I may say so myself. So did I answer your question with the rainfalls? Awesome. See, I did say I'll circle back. And if you look at, let's say, John Connor Online, let me go somewhere else so you guys can see that we have other stuff. Let's go to So this is the John Connor Online interface, and you might find that is, in my opinion, well, actually, I'll go somewhere in Blacktown. Google Maps integration is going on. There's nothing else in the world that's this easy to use, in my opinion. So you guys see here, if you hover over the project detail, that's in Hume Council. And you see the catchments, roof. So if I have this road catchment, it's pretty easy. Everything is loaded up. Were you here for yesterday's lecture? Or you did not? Okay. So if you, I don't have it here. If you look at music, you have 5 pages of variables that you have to change. Click next. Or the new music is like even more complex. My preference here, you don't have to do anything. You change the area. You can't change the percentage impervious because the council doesn't let you, because the base flows are all not applicable. So cool. Would you like to know that the TSS mean for Melbourne for a road is 2.431? I mean, you should read the guideline to find this out, no? No, obviously. And then when you press submit, you don't even have to give it a name. And click. Oh, it will tell you what it is, how many square meters, and how many percentage impervious. Music doesn't do that. so many times I changed the area in music, but I forgot to change it in the name. So then my model had the wrong area, although the title of the node said the right area. It's just give you other examples. The bioretention node. So these are all native. Again, rooftop rape garden is a bastardization of the bioretention node by, square peg round hole kind of situation. But it's definitely not a native node in music. Musically can't handle it. So you can have these values here. But now if I'm going to make this too high, sorry, sir, you can't do that. Computer says no. Obviously, it helps you guys out understand more. Surface area, saturated hydraulic conductivity. You can't go too high. 150 is max. And all sorts of things like that. Again, which you shouldn't know. You don't really need to know. Typically, the music modeling will be the lowest part of your job. And sometimes the most stressful. And if you have a big table with 30 parameters that you need to change, what are you going to change? You're going to read all the 100 pages of guidelines to change them? Absurd. And you can have, let's say, a bioretention. Where are you? You have all the information here for the parameters you need to change. In yellow, the parameters. And then things like TN and orthophosphate. Ah, look at that. In this area is 20. Oh, yeah, it's the new guidelines. Done. I don't have to know. I don't care. Submit. And it tells you in the name 1 square meter EDD 0.3 bioretention. The EDD is this part here, right? How much it fills up before it goes on the overflow. Things like that. Click. Oh, and you probably like this one. Rainwater tanks. Oh my God, so many. The gray ones on-site detention. The white ones are rainwater tank. You spend some time reading that, you'll know more than 90% of the engineers who use music. Just literally read the photo. You press on control and zoom on it. That's it. So that's the kind of stuff that we do. And also, the rainfall is loaded up automatically with all these overlapping. And you can actually use climate change, which is very cool. Does that make sense for you guys? Any questions? At all? Not at all. Well, gentlemen and ladies, look at this. On the left here, you may have something called catchments. Tells you all about the catchments, what catchments are, blah, blah, blah. Treatments. Oh, my God. Primary, secondary, tertiary. Yes. All you need to know is right here. And you have me as well. No, sorry, a legend. Haha. Come on. Here's the legend. It tells you these devices are used to address primary, secondary and tertiary. Ah, oh no, a typo. We should all be shot. Tertiary. Devices removing GP and sediment. Click, 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 click. So you guys get some information about what a gross pollutant trap is. Find sediment and dissolve pollutants. You don't use P. Oh, there's in the legend here you see devices are used to address secondary, tertiary, can be used to address GP, but really shouldn't. And that is the bioretention. It's not great. A lot of information, blah, 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 blah. You get all this data. Oh, look, that's how the thing shows up in music. Enjoy. The orthophosphate and total nitrogen orthophosphate are these values here. You can change these values here if you want, but you should really shouldn't. And if you do, and you get found, that's a big boo-boo. Because these are the decay values. How well the bio reduces the pollutant, right? A fundamental aspect as well of chip it also is modification of the biome. Fundamental aspect of the guidelines. You guys, I'll share with you guys quickly, and then we'll do a model, so we can discuss about creating a model. Fundamental aspect of the guidelines is the reductions have nothing to do with the pre-development site, unless you have to deal with Hunter Water, Water New South Wales, and a bunch of others that implement NORB, neutral or beneficial. Let's not talk about that now. It's not that much. You'll get about it. You'll learn about it. But in on-site detention, you look at what was before, what's after, and the after can't be worse than the before, yeah? Basically. In stormwater quality, you have the reductions. Does anyone know the reductions required? Come on, tell me. No? 80? 70 for GPs. But usually that's not a problem. But most importantly, 80, 45, 45. Yes? No? Anyone familiar with 80, 45, 45? Or 80, 60, 45? Or 85, 65, 45? Or 85, 65, 60? Which you all should, by the way, know apparently, because you have to read the guidelines. Or you can just go here and then it's going to... Oh, crap. I didn't finalize it. Or you can just run it and the model is going to tell you what the targets are. That's a problem because nothing goes here. Targets, 80, 45, 45. Great. There you go. I didn't know, but I found out. In the Great Council of Hume City. How about here? Okay, we'll find out. So the reductions are compared to if you didn't put anything there. Has nothing to do with absolute values, which is not particularly sane to me. So I'm going to give you an example why these reductions are not particularly sane. I'm going to build a road. The road is going to generate 1,000 kilograms of suspended solids, right? Can do, right? Out of 1,000, I have to remove 80%. 800, gone. I've done my job. So how much, please, it's very simple, but I do like your participation. How many kilograms of sediment I'm going to discharge into the environment if I achieve my targets? 200. Ding, ding, ding. Yes, sir. 200. Now, I just built a roof. The roof generates far less TSS than the road. About 180 kilograms of TSS. Do I still have to reduce 80% of that? Yes or no? Somebody tell me. No. Okay, I really would like your participation. Who agrees or who assumes or expects that I still have to reduce 80% of the pollution generated by the roof? Hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Who assumes that, okay, I shouldn't do anything, it's all fine? 1? Come on, you guys have to choose one. You can't just be in there, I don't know. Come on, everybody who didn't lift their hand before, lift it now. Then. You guys, all right. You would expect that in a sane application of some sane rule, the absolute value would have something to do, the absolute value of pollutant concentration would have something to do with the water that you discharge in the environment. I am here to tell you, hello Kafka, those who raised their hands first were right, and I'm sorry you are wrong. I predict that you might struggle in the future because you might expect the world to make sense and it doesn't. Speaking from experience. So, no, you still have to reduce 80%. Makes no sense. Of course. You are penalized for having a better quality water discharged, and why are you penalized? Because reducing the 80% of clean water, of the pollutants in clean water, is way harder than reducing 80% of pollutants in muddy water. Right? Imagine you get muddy water and you have a cotton sock. You put it through the boom, a lot of stuff will get stuck in the cotton sock, right? But now you have the roof and you put a cotton sock and just try to keep nothing. Maybe a little bit of sand, but not a lot. So reducing 80% of something that's clean is very, very, very hard. I'm really sorry. I agree with you. It should make sense. Unfortunately, it doesn't. And those of you who are familiar with Kafka may find in this age, in this time of your lives, that Kafka makes no sense and is a completely insane guy, and you will throw away the book. This is completely absurd. I'm here to tell you that I have done that when I was young, your age. And now, unfortunately, I have reached the sad conclusion that Kafka is a documentary rather than what you call it, fiction, unfortunately. All right, so let's create very quickly we still have some time. So I'll show you how quickly you can do a model that is not garbage. In my opinion, a model that doesn't comply with the guidelines and you just put some values in there, oh, blah, 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 done, that's garbage. Because it's not going to be good for nothing. Let's quickly do one. Okay, somebody tell me, and I'm going to, just you guys tell me, give me a land development. Are we having, let's say we're having 3 townhouses. That's fair? Roughly the roof of a townhouse. Quickly. Roughly. 150 square meters, 200 square meters. 200, right? All right, 200 square meters per townhouse. That means that typically you put into the rainwater tank half of the roof, right? Because you can't control the entire roof. The far part of the roof, bringing it to the tank, is too far, right? Your house is going to be a little shoddy, you know. Just next thing you know, you're going to give gingerbread to children and invite them into your oven. You know, it's like, don't do that. So the house is not going to look right, so just half of the roof goes. All right. So we're going to have here, click, total area 300 square meters. So we're going to go 3 times townhouse. Yeah? Fair enough? All right, clean. Done. Now what I'm going to do, Control-C, Control-V. This is the other side of the roof. I might click right here, edit node, and I say to tank, submit, and then edit node to drain. Now, I'm not going to go through a lot with it, but there's another tool that I'm very proud of. It took me 2 years to come up with this interface, and you will think, really? I'll say yes. 2 years for this interface. This is a rainwater tank demand calculator. First, you need to know how many occupants you have in the area. No, first you need to know what guidelines you apply. Right? Rules of man. But I'm here to tell you that many of these guidelines are not super full. Queensland is quite good. South Australia is very, very good because South Australia allows you any form of like factory, childcare, shop, ground floor, shop, upper floor, like ridiculous, right? Supermarket, theater, I don't know, improv theater, I don't know. It's like everything you can imagine is there. So if you run into something that's non-standard, a school, even a school or something, not a standard house, you go to South Australian guidelines and you get the calculation from there. But you have the indoor occupancy calculator. If you go to New South Wales, you actually have the ability to go to the Census Bureau and figure out stuff. My stuff is really, 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 really good, if I may say so myself. So then you have number of dwellings. We have 3 occupants per dwelling, 2.6. Calculate. I'm going to have 7.8 for the 3 dwellings. Indoor demand water calculator for New South Wales. Oh, look at that. Number of occupants for house, toilets, whatever. So I have single dwelling is total dwellings 3. Total demand rate, liters per dwelling per day. Well, I have 2.6 times, 2.6 here. So it's going to be around 68. Calculate my total demand per kiloliters per day, 0.204. I'm going to forget about the irrigation demand. Boom, I'm coming here. Pack, rainwater tank, where is it? Oh, look at that, it's here. House, it says House. I should have said MD next to it, just for the giggles. So my daily demand, I found it here to be 0.204. Boom, 0.204. I'm going to say 5 kiloliters each, so I'm going to say 15 kiloliters. Volume below overflow is 15 kiloliters. I put this one first, so I didn't like. Okay, you can leave this one. Doesn't matter. Very easy to do, right? Click. This one goes to drain. This one goes to the rainwater tank. Double click, drag, click. Done. Okay, well, all of these should probably go to a, oh, where's my car park? I forgot. I'll have a car park here. If the roofs are 300 square meters, the car park is going to be around 200, 170. Total area, click here. And then, yeah. And then this one goes, oh, hold on. No, this one and this one, all of them would go to, let's say, a bioretention. You see there's smaller amount of things here than in the secondary tertiary than here in the secondary tertiary, because the different council, different values, different everything. Get me? That music doesn't do that. So let's go back here and I'll have a bioretention. I'm gonna make it 10 square meters, filter area 10 square meters, submit, click, and now I'm just gonna see if, okay, oh, check this out. I am very proud of this. I didn't even come up with this, one of my devs did. Right click, add links, boom, haha, so cool, right? You know it. You're gonna love this software and you're gonna super love music. And then for those of you who enjoy a little bit of fun, let's run the model. See? Come on. It's a good nod. Their physics are not great, but I think it's fine. So what do we have here? First of all, haha, that's what happens to stormtroopers when they run, obviously. And the result is everything is green, means you have achieved your targets. You hover over it, 85, 66, 56. That, you click on here, 85, 65. Ooh, Blackdown 165. I did not even know that. Boom, cool. I don't need to know that. Did you guys want to know that? Do you want to go to work and just search for data to data entry into a software? That's what you're engineers for? I don't think so. That's not what I am engineer for. I'm not an engineer to be a data automaton. Pisses me off. Why do I care? Okay, these ones have 165. Great. Hooray for me. Okay, I'm going to do the model to achieve the targets. You, the software, tell me what the targets are. I don't need to go search the targets. You tell me what the parameters that I need to use here are, because I have a brain and my brain is focused on achieving the engineering outcome, not on ding, 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 values into a software. So less than smart. No? I don't know if you guys agree, but I'm very, very angry about it. That's actually why I started building this, because I was so angry. Short Eastern European man. Of course I'm angry. Any questions about this? Yes, no, maybe? Yes. For you guys, yeah. A lot of these things are free, some of them are not. Okay, I've achieved the targets, and then what do? Well, I can introduce the catchments in different ways, right? There's a lot of ways to build the model. I can just add, put them here, put them here. I can even save a template, modify it, upload the template, and load it up. There's a lot of options. I just close it. And I can actually save it as a music model and open it up with music, if you feel so inclined, for whatever reason. I can actually upload the music model to here in MSF and do whatever I want to it. If the music model does not comply with the guidelines, it's just going to tell you and say, hey, this node is not valid. And I can also, for those of you who are enjoying older games, maybe you know this, rap routing, Command and Conquer, Red Alert. If you're playing the Russians, there's a rap routing voice there. We have the rap routing. And when you open the file, this is the type of report that nobody can really reject. Done in 1 second. Now, if you want to do this report with this type of report with music, all the data you introduced in music, you should introduce it in your report too. And don't forget to take screenshots with a snip tool. I am not joking. I did have a discussion with the council who said, your report does not have a screenshot from music. I'm rejecting it. And I said, you can't. And he said, this is in our guidelines. And I said, I've read all your guidelines and all your policy. There's no way saying I have to give you a screenshot from music. Yeah, but it's so easy. No, it's not. you be quiet, get the music model, run it, and if the results are not correct, you tell me. Remember when I can come back and say, you can argue with counsel. Of course. But you need to argue the things that are what? In compliance with the policy and the guidelines. So to give you a typical information about this model, assessor name, assessor email, project name, I didn't put anything. We will give you line, project details, latitude and longitude, screenshot, method template details, statistics, all the information about meteorological template, which typically is not provided in the music model. Source nodes, the data table, everything, total catchment area, all of that. That's everything there. Literally one click. Treatment nodes, fall required through the treatment node, which means that you need in the engineering to have a little bit of fall. If your site is very flat, you can't put a bio in. Rainwater tank, a bio needs 150 millimeters from the intake to outlet, right? So if you don't have that drop, use something else. Rainwater tank, obviously, it's above ground, but it can be underground, who knows? But the fall required is only for the extended detention depth in the rainwater tank because everything else is run through a pump. Treatment train effectiveness result. This is the only thing that anybody could potentially challenge because they could say it wasn't produced through music, and which is why you can run a music model and find the results. And if the results are not compliant, are not correct, great. But I think they will be. But everything else in this project is in this report comes from the MSF file, from the music file. So you can't say it's not right because it's literally an output from the model automatically. Mass balance, treatment name, treatment trains, that's pretty cool. And then if I can actually do this, open link in your tab, and I can view it as guest. Boom, so cool, right? So actually I have on your report, you don't have to send them the model because they can view it online. Typical rainwater tank drawings, what everything happens, the data, typical bioretention, whatever happens, all the data, all the soil characteristics for the model, for the pollution generation and soil, and that's it. So that's kind of what, typically you go to in consulting, this report is going to cost you about 3 or 4 grand and might be less complete and definitely not as right, for sure. So I'm sharing with you guys how things can be done in a way that's automatic, online based. You see, this is the computer for the university. It doesn't have music on it or anything. This is all run online. This runs on a server somewhere. I know where. Somewhere. Any questions? Yes? No? Maybe? Sticks, stones, laurels, flowers.
I think that this is a very good for Mac users because every time I need to run a model, it's Windows-based. I have to bring another computer, so I prefer.
I hope it was entertaining. I tried to make it entertaining. A lot of times people's eyes glaze over if you do a lecture that is not entertaining. Thank you for being here. All right, go to the website, create an account, and read the information. I hope it will be useful for you.
Maybe 5 minutes together.
There you go. I mean, sorted.